In coding, an error message tells you immediately if you're wrong, but in open-ended science, verifying a new idea can take months of expensive lab work. How can we train artificial intelligence to propose rigorous scientific experiments when there is no instant feedback loop to correct its mistakes? The paper Training AI Co-Scientists Using Rubric Rewards proposes a novel solution akin to a PhD apprenticeship. To understand the challenge, consider that unlike math or programming, most scientific research does not have an executable environment to verify truth effectively. The researchers identify that existing language models struggle to generate high-quality research plans because they cannot simply run a simulation to see if their hypothesis holds up. Relying on real-world trial and error is often too slow, costly, or dangerous, particularly in sensitive fields like medicine. Since we cannot simulate the world perfectly, this paper suggests treating the AI as a co-scientist, a brainstorming partner that proposes rigorous plans for humans to refine. To train this capability, the authors leverage the vast archives of existing scientific literature. They use these papers not just as text to read, but as ground truth examples to reverse engineer research goals and the grading criteria needed to solve them. Let's examine the specific workflow the researchers established to convert these static papers into an active training signal. The core method involves a four-step pipeline starting with data extraction, where a model pulls a research goal and a specific grading rubric from an existing paper. A policy model then attempts to generate a research plan based solely on that goal. Crucially, a separate grader model evaluates this attempt using the extracted rubric, and the system uses reinforcement learning to optimize the policy model's ability to satisfy these grades. This workflow creates a powerful dynamic the authors call the Generator-Verifier gap. The student model sees only the research goal and must deduce the necessary constraints, forcing it to think deeply about experimental design. Meanwhile, the teacher or grader has access to privileged information, the full rubric derived from the original paper, which allows it to provide a rigorous signal that guides the student towards scientific validity. The grading mechanism is robust because it doesn't rely on a single metric. The system evaluates plans against 10 specific rubric items unique to that paper's problem, ensuring technical depth. Simultaneously, it checks against 7 general guidelines, such as cost efficiency, ethical safety, and internal consistency, which helps prevent the model from optimizing for technical accuracy while ignoring practical reality. A surprising finding was the failure of standard Supervised Fine-Tuning, or SFT, which is typically used to teach models new tasks. The researchers found that SFT models merely mimicked the style of scientific writing, but produced vague plans that missed key requirements. In contrast, the reinforcement learning approach, specifically using an algorithm called GRPO, forced the model to actively solve the logic puzzle of the rubric, resulting in significantly higher rigor. Now, let's look at how well this rubric-based training actually performed when judged by human experts. The results were compelling. In blind tests with machine learning experts, the RL-trained model's research plans were preferred over the base model's outputs 70% of the time. Even a smaller 30 billion parameter model trained this way was able to compete with much larger frontier models, like Grok 4. Furthermore, humans validated the training pipeline itself, approving 84% of the automatically extracted rubrics as high quality. Perhaps the most exciting result was cross-domain generalization. The authors observed that a model trained only on medical papers significantly improved its ability to generate plans for physics and computer science problems. This suggests the model didn't just memorize medical facts, but actually learned a generalized abstract capability for rigorous scientific planning that applies across disciplines. Despite the success, the approach has limitations. The researchers noted instances of reward hacking, where the model would write excessively long plans just to hit every potential keyword in the rubric. Additionally, while the plans were more rigorous, they sometimes appeared less cost-efficient than simpler baselines, and ultimately, these evaluations are based on expert preference rather than the results of actual physical experiments.